Mr. Carney.
Nerd. The real hero of this story is Mr. W.
Get out of my way.
What?
Oh.
Good.
Either way,
We are going to be talking to you about polar coordinates. More specifically, the integrals and derivatives thereof.
and we will also be talking about how to convert between the y equals x mode and the r equals theta mode, because, well, you need those to use derivatives and integrals.
You know, that's a very good point, Michael. High five. So, wait a second. That's not right.
Try that again.
Yeah. So, oh, that's so much better. Okay.
Wait, hold on.
So, we are going to be talking about polar coordinates, and the first topic is switching between the modes of polar coordinates, aka switching between the r equals a function of theta into y equals a function of x.
The first thing to go off of is that r cosine theta is equal to x, and y equals sine theta. R sine theta, excuse me. Now, one of the tricks that I used for this actually was that if you look at dy over dx and you single out the y and the x, you can transfer this here. So you have sine theta over cosine theta, which, of course, as we know, is equal to tangent theta. So there is a nice parallel between these two subjects. And yes, I am on my knees, by the way. No, I do not spend all my time here.
Okay, so now we've got these two lovely equations up on top that'll stay there for the duration of this video. And so now we've got this equation here, r equals square root of x squared plus y squared. Now you might be thinking, how in the world did we get that? Well, I am going to show you a proof of this equation right here. And so if we take this function right here and start it over here, x squared plus y squared, and that's, if we input these two equations into these two, x's and y's, then we will get the equation r cosine theta squared, which is x, plus r sine theta squared, which is y. What we can do with this is distribute out the square. And so, now what we can do with this is take out an r squared from both of these functions right here. And so what that will give us is r squared equal times the cosine squared theta plus sine squared theta. And this might look a bit familiar to you people, as it should, because cosine squared plus sine squared, as most people do know from trigonometry, is just equal to 1. And so we get ourselves x squared plus y squared equals r squared. We got a nice neat little function right here. And then we can just take the square root of both sides, and then we got ourselves a little r equals square root of x squared plus y squared. And there should technically be a plus or minus on there, but we are going under the assumption that r is positive for the remainder of this video.
Okay, so for this equation, you're going to begin with this little bit. You're going to begin with y over x, which, using these two equations, we can sub in r sine theta and r cosine theta for y and x respectively. Now, looking at this equation, of course, the r's will cancel out, leaving you with y equals x, y over x, excuse me, equals sine theta over cosine theta, which, as we know, equals tangent theta. So, of course, we can just there use the inverse of tangent, which will thus give us theta. Derivatives of polar equations. I'm not entirely sure this was taught in classes here. It certainly wasn't on the AP test, but, let's do it anyways because, math is fun. So these actually derive from these functions up here. We will start actually by looking at this in two parts. We'll look at just the numerators and just the denominators. So first we'll look at dy equals dr over d theta sine theta plus r cosine theta. Now, this will actually derive from the equation y equals f of theta sine theta, which f of theta is right now subbing in for r. So when we take the derivative of this, we will actually just get a simple product rule. It makes much more sense, I think, than that mess. So what you'll get is dy over d theta equals f prime of theta sine theta plus f of theta cosine theta. Because if you could back up, that'd be fantastic. I hope you're not blocking the shot entirely. And so now we can substitute in r's, and as you'll see, we will actually get the numerator of the right side of the equation. Then we go having this. Merry Christmas. Having this equal dr over d theta sine theta plus r cosine theta. And voila, we have, first off, the numerator of the equation. All right, now we're going to be doing the x portion of this derivative. So we'll now be looking at only the denominator. So we'll once again begin with just x equals f of theta, and this time we'll use cosine theta because we are substituting directly off of this equation. And let's take the derivative again, which will give us dx over d theta equals f prime of theta cosine theta f theta sine. Once again, we will be substituting in various forms of r for f of theta. So we get, as the final product, same as the denominator up there, dr over d theta cosine theta plus r sine theta. And that'll be equal to dx over d theta. And since we have two independent equations, one that is dy over d theta over dx over d theta, so we'll have actually dy over d theta all over dx over d theta. The d thetas will cancel out, letting this equal dy over dx.
Okay, so now we are going to do the integrals of r equals theta function. So to get the integral, the proof is more conceptual in this lesson than it is actual physical proof. But nonetheless, there is still a physical one out there if you look it up. So now, to get the integral equation for r equals theta graph, you have to go all the way back to Riemann sums. So now, to get the Riemann sums of a normal y equals x planar graph, you just use rectangles to approximate the area under the curve. But now, with r equals theta functions, you're going to have to use sectors of circles with r being the radius, and d theta is actually the angle measure of each sector. Got that? Good. So now, with this knowledge, the area of each single sector is actually going to be pi r squared. May look familiar so far, but we're going to add times d theta all divided by 2 pi. That will give us the area of a sector of a circle. Now, in order to, we can simplify this a bit, and we can get these little pi's out of here. No one likes pi anyway, it's kind of gross. So then we can take this 1/2 out and get a little 1/2 r squared times d theta. This may look familiar. Okay, now, so we can get from here to here by taking the integral from a to b. And this is given the fact that the limits of our integral are a times f of a and b and f of b. I may have said times in this. That is not the case. It is just a points on the r equals theta function, doing the endpoints of the curve you wish to measure the area under. And that is why this is the area under the curve for r equals theta function. Thank you, Michael.
So, ladies and gentlemen, we've reached the end of the presentation. Here we have all of the equations that we used. Enjoy the rest of your year in calculus. The rest of the year overall, it's 2 or 3 days at this point, so see you all around and Mr. Gingrich, well, thank you for another good year, and goodbye.
Bye-bye.
It's a trilby!